So our speaker today is Raffael Stenzel with Infinity One Comprehension schemes. So you can start whenever you're ready, Raffael.
I am ready right now. Hi, thanks for tuning in to my Blackboard talk. So in this talk, I want to introduce a notion of comprehension schemes for Infinity One category theory. And the whole concept of comprehension schemes has been introduced to categorical logic, ordinary categorical logic, by Lauvier, and then later in more generality by Benabou, and then by Johnston in the 70s, at least, as far as I'm informed. We will lift this notion and all the applications and even more applications and examples to the world of Infinity One categories. So the idea for today is, first of all, just set up the necessary notions. So comprehension schemes will be properties of fibered infinity categories. And so I will just give a quick definition of fibered infinity categories and the Grothendieck deconstruction that there is to state the equivalence to indexed infinity categories. But the vast majority of the time will be spent today on the second part, which is just motivate the notion, the definition of comprehension schemes, and then give the necessary definitions, the most important instances, and examples and applications. And then if time permits, we will look at the same thing at the level of model categories. So the question will be, well, before we started with an infinity category C and took an indexed infinity category over it, and then we can ask the question, well, what if C is the homotopy infinity category of a model category M? And are there certain homotopical algebraic results that kind of relate to what we did before, right? First of all, to the preliminaries. So whenever we say in the following hour infinity, we mean infinity one, right? So there's no infinity n involved here. The most basic notion here will be the infinity category of spaces, which will play the role of sets, right? It's the infinity topos that is underlying everything we do. And more generally, or more specific, depending on your perspective, there's the infinity category of small infinity categories, which we denote by cut infinity. And then given an infinity category C, a C index infinity category will just be a contravariant functor into infinity categories. So we think of it as a C indexed collection of other infinity categories. And whenever I has a terminal object, we think of the evaluation at that terminal object at I as the underlying infinity category of that indexed infinity category. We can collect all these things together to form the infinity category of C indexed infinity categories. This is by definition an infinity one category. It would be more natural for structural reasons to define it as an infinity two category, but this will not play any role in anything we do today. So this will be just considered as an infinity one category. Similarly, we can look at the group Riedel versions of this. So a C index infinity groupoid is a contravariant functor into infinity groupoids, that is spaces. So in other words, these are pre-sheaves over C, right? Which we denote by C hat. All right. Now, just a handful of examples that we will use in order to give examples later for comprehension schemes. So a very rudimentary example is if we are given an infinity category C, then we can consider its naive indexing over cut infinity and over S respectively. So this is just given by looking at functors into C, right? Both give respective contravariant functors. And if we evaluate both of them at the terminal object, we retrieve C itself, right? So these are natural generalizations of C in the context of indexed infinity category theory. Another example is we can index C over itself in a very canonical way, namely if C has pullbacks, then we can consider the slice functor. Again, if C has a terminal object, we can evaluate a determinable object and retrieve C itself, right? So this is a natural generalization of C over itself. In the spatial case, well, we have two examples now. If we apply both of them to the case when C is the category of spaces itself, then we can look at its naive indexing over S and its canonical indexing, which is also an indexing over S. And in this case, the two are actually equivalent by a special case of the Grothendieck construction, right? All right. Another tool is the change of base. So if we are given a C index infinity category and we have a functor into C, then we can just pre-compose with F in order to obtain an index infinity category over D. And lastly, to give an example of a very important example of index infinity groupoids, they are the representative presheaves, right? They will be somehow the reference structures for everything we do in the following. All right. Now, in order to move in between from indexed infinity category theory to fibered infinity category theory, we will use Lurie's framework of straightening and unstraightening, which is an infinity categorical version of the Grothendieck construction. Right. So he constructed adjoint equivalences between the infinity category of Cartesian vibrations over C, which are an analogon to the Grothendieck vibrations, and indexed categories over C. And this restricts to an adjoint equivalence between the right vibrations over C, which are analogon to the discrete vibrations, and the presheaf over C. And this allows us to give us to define what it means for a right vibration to be representable, which just means that its associated straightened presheaf is representable, right? We can compute them in the following way. Up to equivalence, right vibration is representable if and only if it is of this form. So it's the source vibration of a slice, right? So they all look this way. And the straightening construction allows us to give us to define another construction, namely we have a core functor from infinity categories to spaces. So what we can, which just means we take an infinity category and consider the largest infinity groupoid contained in that infinity category. And so what we can do is we can take a Cartesian vibration and straighten it and post-compose it with the core functor. And then we can straighten it back and we obtain a right vibration. And we will call this right vibration the core of P accordingly. A way to construct it as well is just, it can be constructed as a sub-vibration of P. So we can construct P cross as a sub-vibration, which is given by the same objects as E has. Its Cartesian morphisms are exactly the Cartesian morphisms in E, but its vertical morphisms are just the equivalences, the vertical equivalences in E, right? So we throw everything non-invertible out in the fibers. Yeah, so now we can revisit the examples that we had before and consider them as fibered things over our base category C. So if we take the naive indexing as we did before and post-compose it with a core functor, we obtain a presheaf over cut infinity, which is just the representable over C, right? The Hom spaces between two infinity categories are just defined, at least in Lurie's book, as functors, and then we take the core of that thing in order to obtain actually an infinity category, a space, right? It should be it's an infinity one category, so it should be enriched in spaces. Yeah, and the straightening is just the representable right vibration over cut infinity represented by C. Similarly, if we restrict that representable to spaces, its unstraightening is again given by something that's not quite representable. The notation is a bit misleading because C is not an infinity groupoid, right? If it would be an infinity groupoid, this would be a representable. This is more like we can embed spaces in infinity categories, and this is like the comma infinity category from the embedding over the object C in infinity categories. More generally, we don't have to go to spaces, we can go to infinity categories. And so we have the naive indexing, and we can unstraighten the thing and obtain some Cartesian vibration. And by lack of a better notation, we can just use a very suggestive one in borrowing it from type theory, which we just denote by, well, it's a space together with something in a fiber, which is a functor from that space into C. And we call it the infinity categories of families of C, adopting the nomenclature from ordinary category theory, right? There, if we have one category C, we can consider this naive indexing of a set. And the Grothendieck construction of that thing is just the from C, it's the Grothendieck vibration of families in C. And again, if we do not do this over set, but don't do this over spaces, but over all infinity categories, we again obtain some unstraightening, right, which we can denote in the same way. And the latter is given by functors into C. So if we post-compose it with a core functor, we exactly obtain the presentable of C. And so by definition, if we take the core of that thing, we just obtain the representable we had in the beginning, right? So just a little gymnastics with these notions. All right, then the other example that we had was the canonical indexing of C over itself instead of over spaces or infinity categories. And somebody has the sound on. Thanks. Yeah, if we take the canonical indexing of C over itself and we straighten the thing, we obtain the target vibration of the arrows of C over itself, right? And for that reason, we will call this target vibration the canonical vibration of C. So this will be one of the very important examples. And lastly, how does the change of base translate? The change of base translates to just taking fullbacks, which is extremely useful to compute unstraightnings of a given indexed infinity category. So if we have an indexed infinity category I, we can unstraighten it. Then we can take the functor f into it, pull back, and this will give us the unstraightening of the change of base along f of I. Now, as a special case, we can unstraighten the identity over infinity categories, and this gives us the universal Cartesian, it gives us the universal co-Cartesian vibration. And if we opt that thing, we obtain the universal Cartesian vibration. And it is universal in that sense that every Cartesian vibration, every small Cartesian vibration, but let's just skip this for a second, that every small Cartesian vibration is the change of base along its own straightening of the universal Cartesian vibration. So we can depict this in the following way. If we are given P, we can straighten it. We can take the pullback of the corresponding functor and obtain P back again up to equivalence. All right. And in a similar way, there is a universal right vibration over the infinity categories of spaces, and every right vibration, every small right vibration is the change of base along its own straightening up to equivalence. All right, this sets up all the preliminaries that we need. So we can go on and talk about comprehension schemes. So the definition itself is is a bit opaque, and so I want to give a motivation that in the beginning will sound a little esoteric and eerie, but we will make them so bear with me for those 2 minutes, and then we will introduce precise notions. So the notion of comprehension scheme is comes from set theory originally, right? And if we remember, what does it mean in set theory? We have the axiom scheme of separation, or in other words, restricted comprehension. And it says that if we are given a set X and some first order formula phi, or say a class S, then if we restrict those two things, if we intersect those two things, we obtain a set again, right? So the set theory is closed under some sort of structure, right? So in order to make the necessary leap to higher category theory, we take a step back and try to understand comprehension schemes from a very general point of view. So we say that in order to explain comprehension schemes is we are given a background theory, some sort of meta-mathematics, right? And then we are given some model of that meta-mathematics that formalizes some part of it, not necessarily everything. And then we might be given some logical structure over that model. And given that data, we say that model M satisfies the comprehension scheme associated to S if whenever we apply that structure S to an object in M, the resulting thing can be internalized in M, right? So this sounds very esoteric, but on the next slide, I will give a little dictionary what that means in set theory and what that means now in our context, all right? Putting those two, and also before we continue, I should say everything I said so far is basically contained in Lurie's book, right? So this was all kind of public knowledge, and everything we do now is what I did in the last, like from the beginning of this year. Everything that has to do with comprehension schemes. All right. So what is the meta-mathematics we consider? In set theory, it is just naive set theory, right? And the notions there are the proper classes. And in higher category theory, we might say the meta-mathematics is just naive category theory. In this case, naive higher category theory, right? Now, a model of a fragment of mathematics here is some set theoretic universe, or just some model of set theory, right? With a formal membership relation. And here, our model of category theory will be not just an infinity category, but it will be an index infinity category over some base C, right? So far, we don't make any assumptions on C itself or on the index infinity category E. Then what is a mathematical object? A mathematical object in set theory is a set X in our set theoretical universe. And in our case, it will be not just an object in the index infinity category theory, but it will be any sort of diagram, right? So because we basically move from properties to structures, right? And an object will be some structure in that index infinity category. Then the external structure here in set theory is the class S that we want to intersect with our set. And here it will be a diagram extension, right? So we have a diagram over some infinity category I, and then we might extend that category I to some J and wonder about the structure that extends X along that functor, right? So indeed, the induced structure over a mathematical object will be the intersection of S and X in set theory. And here we consider the pre-sheaf of all diagrams in J that extend X over C, okay? And then what does comprehension mean? In set theory, it means that induced structure, S intersected with X, is again contained in V, right? So it is a small set in this sense, right? And in higher category theory, it will mean that this pre-sheaf of structure will be representable over C, right? So there is a translation between smallness and representability. Indeed, Benabou in his paper back then interpreted the conclusion from sets into proper classes as a Yoneda embedding, and then considered the sets as representables in proper classes. All right, so keeping this in mind, we will give formal definitions now. So for everything we do, we fix some infinity category C, right? And now we want to consider some Cartesian vibration over C and define that define the diagrams that we consider in the diagram extensions. So given a simplicial set I, we indeed do this for simplicial sets, not just for infinity categories. We can define the rectangular diagram infinity category in the following way. We can just take P and exponentiate it by I, which is again a Cartesian vibration, and then we can take its core. That is the composition on the right-hand side. Now this thing is a right vibration, and it consists of all diagrams in E, all I-shaped diagrams in E, but only the Cartesian natural transformations. So all the natural transformations that are pointwise Cartesian. And then we can pull the whole thing back along the diagonal, which then gives us, again, a right vibration, right? So this will be a pre-sheaf over C. And its objects are the fiber-wise I diagrams in E. And the natural transformations, the edges in there, the morphisms, are the natural transformations which are collectively Cartesian over one single arrow in C. Right? So Johnston, in ordinary category theory in the elephant, did define such a notion of rectangular diagram category in a slightly different way. So this generalization is not quite faithful to his. And I only did this because the proofs turn out much nicer when you define it in this way. But the notion of comprehension will be equivalent in all relevant examples, right? So if we define rect IE in this way, then we can wonder what does this correspond to as an indexed infinity category theory, and it has a nice description. Yes, sure, sorry. As a special case, when we look at points, rectangular points in E, then this is just the core of E, right? So it has all objects in E, and the morphisms are exactly the Cartesian morphisms. So as an internal category, if we start with an index category I and we unstraighten it, and then we take rectangular diagram in there, and then we straighten it back, then this is indeed just the indexed infinity groupoid of fiber-wise I diagrams, right? We first take an object C, consider its fiber IC. We take I diagrams in there, and then we make the whole thing into a presheaf. All right. So having this at hand, then we can define the notion of G comprehension to be the data of a functor I to J. And then we say that a Cartesian fibration is G comprehension if the restriction of these between the rectangular diagram categories has a right adjoint. Now, this is what I mean by it's a rather opaque definition, right? How can we draw this back to what we were talking about before? Well, if we are given a Cartesian fibration P and a functor G, right, then we can just take one rectangular diagram X and consider the associated comma category. Now, what it means to have a right adjoint means that these comma categories have, for every X, have a terminal object, right? This is the formulation of having a right adjoint via universal arrows. Now, if we consider the comma category, the upper arrow from the comma category into the slice over X, we can post-compose this thing with P over X and obtain a mapping to the slice over PX, right? And it turns out that at least if G is a monomorphism, this composition into the slice will be a right fibration. So this will be indeed a presheaf, drawing back to the table we had before, right? So there is, oh God, this did not work out, sorry. So there is a lemma which says that at least if G is a monomorphism, then a Cartesian fibration P has G comprehension if and only if for every diagram X, this infinity category of diagram extensions is representable over the slice. Now, if G is not a monomorphism, we don't have the same lemma, but if G is an epimorphism, there's another way to interpret the notion of G comprehension, namely in terms of definability of subfibrations, which was also something Benabou considered. And every functor factors as an epi and a mono. So every G comprehension for every functor G can be interpreted as a combination of those two. But in fact, all examples we consider today are monos, and only one or two are epis, but none of them are neither. Yeah. So the general strategy to prove a comprehension scheme will be to show that these total infinity categories have a terminal object, right? And now we will go into a couple of examples to give you a feel for that notion. So first of all, every Cartesian fibration is G comprehension for equivalences, right? So if G is a recategorical equivalence, then every Cartesian fibration has G comprehension for that thing. In a trivial way, I mean, because they preserve them. Okay, then we can define the most, basically the only two ones we will be bothered about in this talk. On the one hand, we consider the comprehension for the map from the empty set into the terminal object, and we say that P is small if it has the according comprehension scheme, right? So what does that mean? If we just unfold the definitions, it just means that the core of P has a terminal object, right? And because this thing is a right vibration, there is a lemma that says that the total space of a right vibration has a terminal object if and only if the right vibration itself is representable, right? So this is smallness, and there's a notion of local smallness, which is comprehension with respect to the boundary inclusion, right? So what that means is give me any two objects, T1 and T2, in the same fiber, then there are two other objects together with a vertical arrow in between them, such that those two objects. I will draw a picture later, but we have T1 and T2. We have two other objects and Cartesian morphisms into T1 and T2, and we have a vertical arrow between those two objects, which is in some sense universal, in the sense that whenever we have any two other objects which have Cartesian morphisms in our original 2 points, and there is a morphism between them, then that morphism maps into that universal morphism, we hereby assume. So both of these comprehension schemes have also been were already fundamental notions considered by Benabou in the ordinary setting. Yeah, and they just generalize naturally. All right, so let's consider examples with these two instances. So we can consider representable vibrations over any category C, and one can show that they're locally small in the sense we just defined, if and only if the diagonal here has a right adjoint, right? So the right-hand side here is just the rectangular diagram category over 2 points, and the left-hand side comes from considering rectangular diagrams over the walking arrow, but because this thing is a right vibration, these are basically vertical equivalences, and we can show that this is just the slice itself. But the diagonal has a right adjoint if and only if equalizers with for arrows with domain C exist, right? So we get the consequence that all representable vibrations over category C are locally small if and only if C has all equalizers. Now we can look at where the name small and local small come from. Namely, I didn't really distinguish between small and large infinity categories at this point, and I will not in the future. But just for this one example, we can consider C to be a potentially large infinity category, so it's a simplicial class. And then one can show that C is small, meaning it's a simplicial set, is an infinity category, or locally small, meaning its home spaces are simplicial sets, if and only if their vibrations of families are small or respectively locally small in the sense just described above. So smallness and local smallness are both generalization of these smallness notions. Now in this case, of course, smallness implies local smallness, right? But this is not a general case for these more abstract notions. So we can look at another kind of degenerate example, namely the map into the terminal object is a Cartesian vibration for every infinity category C. Now, its Cartesian edges in this case are exactly the equivalences. Then one can see that the rectangular diagrams of shape I are just basically the functors from I to C, where the natural transformations are just equivalences, right? So this is just the core of the functor category. And then one sees that this vibration is small if and only if the core is contractible, the core of C is contractible, and it is locally small if all its home spaces are contractible. And this gives you gives you examples of Cartesian vibrations which may be small but not locally small. So smallness does not necessarily imply local smallness, right? You can consider some other free monoid over one object or something. So something that has no non-trivial isomorphisms, but non-trivial non-invertible maps. And then there is another important example, namely the canonical vibration. And then you can show, as in the ordinary case, that the canonical vibration is locally small if and only if C itself is locally Cartesian closed. All right, and just to remember what that means, an infinity category C is locally Cartesian closed if, well, all its slices are Cartesian closed, which means for every two objects in every of its slices, the product in there has a right adjoint, which can be phrased in this way, right? So it can be phrased in representability of a certain pre-sheaf. The proof is just quite straightforward, but very, very long and annoying. But the idea is very simple because it's the same idea as in the ordinary case. Namely, in order to show this, you want to show that the two pre-sheaves are equivalent, right? So we know that the vibration is locally small if and only if this comma category is representable, and it's locally Cartesian closed if and only if these pre-sheaves on the top line are representable. So we want to compare these two pre-sheaves, and one can do so by using that the class of vertical arrows in the class of Cartesian squares yield a factorization system on the arrow category, right? As for every Cartesian vibration, you have that the Cartesian arrows and the vertical arrows up to equivalence give you a factorization system on the total total infinity category. So as a picture, just object-wise, right? We might be given a map F. So a map F as an object in the unstraightening on the top, right? So it is a map from the pullback. So we are given a map Z, and we pull back Z along X, right? This is our domain, and we want to consider a map from F into Y in the slice, which is just the same as a square from the pullback into Y over Z, right? Now, if we are given such a square, we can factor that square into a vertical arrow V and a Cartesian arrow, which is the top face of that prism. And this is exactly an object in this comma category, right? So an object in the comma category is just two objects, which are x times z and y times z in this case, together with Cartesian arrows into x and y, which are the two Cartesian squares, and a vertical arrow between them. And yeah, you can show that universality in both cases kind of translate into each other. All right, so having these examples at hand, we know that certain vibrations satisfy certain comprehension schemes, so we might wonder, well, maybe there are some closure properties that we can prove, so to deduce one comprehension scheme from the other. So we can consider, so given a Cartesian vibration P, we can consider the class of all functors between simplicial sets such that P satisfies the according comprehension scheme. And then there's the following lemma, that the whole class contains all weak categorical equivalences. We have seen that, well, I mentioned that. And it's further closed under composition and under pushouts along monomorphisms. If we restrict to the monomorphisms, then we can show that it's closed under arbitrary pushouts. And actually, what I did not use anywhere, but which is also, I mean, noteworthy, is that the class of monomorphisms in there has the right cancellation property. So if we have the composition of two monos is in there, and the first one of them is in there, then the second one is in there too. All right, so what are we doing here? Yes, so as an example of these, so as an application of these closure properties, we can consider more comprehension schemes, which have been considered in ordinary category theory too. Namely, on one hand, there is a definability of invertibility for arrows, which is defined to be the comprehension scheme for the inclusion of the walking arrow into the walking iso. So it kind of is an internalization of am I an ISO or not, right? We want an object that classifies that statement. Then there is definability of equivalence between parallel arrows. So we want an object that figures out if two arrows are equivalent or not over some fiber, which is the comprehension scheme for the two parallel arrows into the walking arrow. And we can do this for arbitrary n. So we can consider equivalence of parallel n cells by doing the same thing for n cells. So it's a bit awkward that these are kind of globular definitions while we work in a simplicial setting. But they turn out to be rather irrelevant anyway, because we have the following proposition. Given any Cartesian vibration, then definability of equivalence of n cells implies delta n plus 1 comprehension. So we can kind of move a level up. And if we have equalizers, which in most of our examples we will be interested in, then on vice versa, delta n comprehension implies equivalence of parallel n cells. So we have like a staircase to go up, right? So as a corollary, you see that if p is locally small, which is delta 1 comprehension, then it has delta n comprehension for all higher n. So the higher data in this case follows. And we can also show that if p is locally small, it also has this definability of invertibility, which is a generalization of the ordinary categorical statement. Yeah. So what we see, what we can infer from this is that a vibration is small and locally small if and only it has J comprehension for all monomorphisms between finite simplicial sets. The reason is, of course, one direction is obvious, because smallness is, well, the mono from the empty set to the terminal object, and local smallness is the boundary inclusion. And vice versa, if it is locally small, we see that it has delta n comprehension for all higher n, and smallness gives you the comprehension for the empty set to the terminal object. But every monomorphism is built by cells of these, right? Is built by pushouts of finite compositions of these things. And in the prior lemma, we have seen that the class comp P is closed on those. All right, so the theorem I want to get to in the following, which will be quite at the core of what follows, is concerns internal infinity one categories. So just a quick sketch of the definition of what an internal infinity one category theory, internal infinity one category is. In order to define these things, we will assume that C is left exact, so it has all finite limits. And we consider the category of simplicial objects in there, right? And yeah, abbreviated in the following way. Then a Siegel object is a simplicial object in C, such that its associated Siegel maps are equivalences in C. So these give you a notion of composition, yeah, these things give you a notion of composition, of higher composition in there. And then one says that a Siegel object X is complete if a certain map is an equivalence. So having a notion of composition in that Siegel object, we can define a notion of equivalence, of internal equivalence in that object. And completeness relates this internal notion of equivalence with the external notion of equivalence in our category C. And yeah, this is a way to phrase this. So complete Siegel objects will be our notion of internal infinity one category in C. And then we denote the full infinity subcategories of simplicial objects by SC and CSC respectively for Siegel objects and complete Siegel objects. All right. Accordingly, we can define a Siegel groupoid to be a Siegel object in which every arrow is invertible. And a way to phrase this is there is a natural map from the equivalences in X to all arrows in X. And then we want this map to be an equivalence itself. So every map in X can be proven to be an equivalence. And then accordingly, we obtain a full infinity subcategory, which we call SGPD of C. All right, so having an internal notion of a category in C, we can externalize that thing. So this is a construction that existed for ordinary categories, and it exists for higher categories as well in the following sense. Having the Yoneda embedding for C, we can consider the push forward on simplicial objects, right? And the codomain of that thing can be just curried into being contravariant functors into simplicial objects in spaces, right? And if we restrict that push forward to complete Siegel objects in SC, then we can show that the image of that thing will give us contravariant functors from C into complete Siegel objects in S. And we have an equivalence between complete Siegel objects in S and actual infinity categories, proving that so complete Siegel objects in spaces are internal categories in spaces, right? And internal category theory in spaces should be just infinity category theory. And by that model categorical result of Shirai and Turney, you have actually an equivalence from complete Siegel objects in spaces and infinity categories. And we can just push forward along that equivalence to obtain functor from complete Siegel objects in C to indexed categories over C, right? So this composition we denote to be the externalization from internal infinity categories in C to indexed categories over C. So more heuristically, we can think of the externalization of a given internal category X as the functor which takes an object C to maps into that complete Siegel object. So the zero simply C's are just maps from C into X0, and the arrows are maps from C into X1, and so on, right? So the type this equation doesn't type check, but as it's written down. But there is a way to make a type check, and this is the intuition we have about this functor. And indeed, if we start with a one category, then the complete Siegel objects in C are just the usual ordinary internal categories in C, and the externalization as we defined it is just the one categorical externalization as studied in ordinary category theory. Oh yeah, the second reference is Jacob's book on categorical logic and type theory. I'm sorry, I did not see that this is cut off. All right, and then we can instance check if something is a groupoid by either checking it internally or externally. So a Siegel object X is a Siegel groupoid if and only if its externalization is a presheaf, right? So there is a transfer of structure between internal things and external things.
Sorry, Raphael, can I ask a question?
Of course.
In your remark, the first point, is it similar to say that you identify X with its associated prederivator, or it's completely different?
I do not know.
Okay.
I do not know. Yeah, I do not know. Maybe I'll catch up on that later after the talk. Yes, and just a remark. So the externalization as such has not been defined in the literature as far as I'm aware of it, but the process itself, the functor itself, not giving it that name and not giving it that, not being embedded in that framework, has been considered by Razek. So he has this paper about complete Siegel objects in infinity one categories, and he considers also Cartesian vibrations over them, and then he has a process to assign to a complete Siegel object a representable Siegel Cartesian vibration in his language. And if you translate from his language over complete Siegel spaces to quasi categories, then these are exactly the externalized ones. So in fact, some of his results can be just used in this context. And now there's the question that if I am giving a Cartesian vibration, can I check whether it is a complete Siegel object whose externalization P itself is, right? It's a representability problem, basically. And it turns out, yes, infinity categorically that works out perfectly well. Namely, the theorem is that a Cartesian vibration over a category of pullbacks is the externalization of some internal category if and only if it is small and locally small. And this is a result that fails in ordinary category theory. So if you look in most of the treatments about these sorts of structures on Grothendieck vibrations, like the According chapter in the Elephant, or Schleicher has a long paper about all sorts of notions involved there. Then they always have certain gymnastics to do, because smallness in this particular case is not a very well-behaved notion ordinary categorically, because it's not preserved under equivalence of categories. And in our case, it is. So kind of the problem in ordinary category theory that arises here, if you look into it, is that the category of categories in that case is enriched over set and not over itself. And you end up having strict identities where you actually want equivalences. And in infinity one category, you do not have that. Everything is an equivalence. At no point whatsoever you in fact talk about strict identities. So as a special case, I mean, this is to no surprise, if P is a right vibration, then P is small, meaning it is itself a representative pre-sheaf because the core of a right vibration is itself. Then it is small if and only if there's a complete Siegel groupoid whose externalization it is, which basically just means P is small if it's representable. This is just a fancy way to state the obvious. It just pops out, and it's nice as a juxtaposition of these two things. So as a corollary, we can make this a bit more, we can phrase this a bit more differently, namely, if we consider the full infinity subcategory of small and locally small indexed infinity categories and see its pullbacks, then the externalization construction gives us an equivalence of infinity categories between the internal categories in C and the small and locally small infinity categories over C. And the reason for that is just that the externalization functor is fully faithful. So then we restrict to the image and we obtain the equivalence. And fully faithfulness here, we can indeed, this is the one time I use explicitly one of Razek's results who shows this. Yeah, and as a corollary, we have seen that a vibration is small and locally small if and only if it has J comprehension for every finite mono J. And so we see that if C is pullbacks, then this is again equivalent to being the externalization of a complete Siegel object X. All right, now let's apply this to one Cartesian vibration of particular interest, namely the universal Cartesian vibration pi op. And it's we can also apply this to its companion, which is the universal right vibration. So we have the following proposition that we can show, namely that the universal Cartesian vibration has the initial map comprehension for every initial map, right? So for every simplicial set I, the map from the empty set to I is comprehended by the universal vibration, and the according right vibration that we have to consider is represented by IOP in a yeah, I mean it's the obvious candidate in this case. So what does that mean? Well, if we look at the special case I equals delta n for varying n, then we see that the rectangular simplicial diagrams in the universal Cartesian vibrations are represented by the accordingly shaped diagrams in the infinity category of infinity categories. So what one can show by just using the closure properties I wrote up before, that the universal Cartesian vibration is small and locally small. If one does more work, one can in fact show that these equivalences on the top prove that the whole Cartesian vibration is the externalization of the complete Siegel object given by delta bullet. So I referred in the abstract, I referred to this in the abstract as the freely walking chain, because right at every level it's the freely walking end chain. And this is very nice because if you remember, Lurie in his book had a result that the Cartesian, no, sorry, that the universal right vibration is in fact representable, right? Because the right vibration corresponds to the pre-sheath, and pre-sheaths can be representable, and he showed that it is so, represented by the terminal object in spaces. Now, the universal Cartesian vibration cannot be representable because it's not a right vibration. It is only a Cartesian vibration. But it is representable in the best way possible, meaning it indeed is representable by an internal category. So let's keep this in mind and look at the way we can move from one comprehension scheme to another. So there's the following lemma. If we have a Cartesian vibration and we change its base to another category, then whenever that change of base is a right adjoint itself, pullback preserves comprehension schemes, right? So the pullback satisfies every comprehension scheme that P itself satisfies. Whenever that functor we change of base along has a right adjoint. So this was a lemma also that holds in the ordinary case and translates to the infinity case. So as an example, we can consider the universal right okay, in this case we consider the universal left vibration and the universal co-Cartesian vibration, and one can construct the universal left vibration as the pullback of the universal co-Cartesian vibration along the canonical embedding from spaces into infinity categories. And this functor has a left adjoint, right, by building the free infinity groupoid over infinity category. Now, if we op everything, right, this inclusion has a right adjoint. F op is a right adjoint to I op. And so this means that the universal right vibration satisfies all comprehension schemes that the universal Cartesian vibration satisfies. So in particular, it is also small and locally small, right? One can be a bit more precise here and prove the following lemma, that again, if we have a functor with a right adjoint, then if we have a complete Siegel object in C, sorry, and we take its externalization and we pull back the externalization, then the pullback of the externalization is just the externalization of its image under the right adjoint, right? So there is like a commutativity here. So as a corollary here, for the last example, we see that the universal right vibration is the externalization of the complete Siegel object, considering the freely invertible chain in spaces. Now, that thing is contractible in spaces. And so it is contractible to the terminal object, in fact. And so we retrieve, in this conceptual way, the statement that the universal right vibration is presentable by the terminal object, because that complete Siegel groupoid is contractible. Yeah, that's what I said. All right. So if we keep on applying this last lemma, so this upper lemma here, to the universal Cartesian vibration, then this gives us a way to compute the straightening of indexed infinity categories whenever they have a left adjoint, right? Because it's just the externalization of the image under the right adjoint of the freely walking chain. Now, in fact, there is a converse direction too whenever C is complete. So if C has all limits, then we can show that a C index infinity category is the externalization of a complete Siegel object if and only if it has a left adjoint. Here left because we start from C op and go into cut. If we go from C to cut op, we have the right adjoint statement before, like before. Yes. So in particular, if C is presentable, right? What we see is, I mean, this then shows us that C is the externalization of complete Siegel object if and only if its straightening preserves limits, because the right adjoint functor theorem, right? So if we restrict this to right vibration, this is exactly the fact that the limit preserving pre-sheaves over presentable infinity categories are exactly the representable ones. Yeah. Ah, yes, exactly. So again, as a corollary, obtain that whenever we have an internal category in some C, we can externalize it. We know its externalization of this form has a right adjoint. And so we see that every internal category in a complete infinity category C satisfies all comprehension schemes that the universal Cartesian vibration satisfies. All right, so much to all these to the comprehension schemes, the definitions, the examples. I will not be able to make it to the model categorical considerations, I'm afraid, but I will say a few words to the relationship to the notion of univalence, because there is a strong connection between the notion of completeness for Siegel objects and univalence, as was studied at different parts of the literature, and has been made a definition in Razek's paper, the one that I referred to before. And we can, in order to make that definition to comprehend, to the relationship to comprehension schemes, we can consider again a category with pullbacks, and we can define comprehension affinity categories in the sense of Jacobs, right? We can just take his definition for ordinary categories and just put it in our framework. So we say full comprehension affinity categories of C is just a full subvibration of the canonical vibration. I will not say exactly what the subvibration is, but it's more or less it's more or less self-explanatory, modulo technicalities. And the example I want to look at is if C is locally Cartesian closed. Actually, at this point, we don't even need this yet. We can take a map Q and C, and we can look at the class, like the class of reindexed families, right? We can look at the full subcategory in the arrow infinity category, whose objects are maps which arise as pullback of Q in some way, and take the full infinity subcategory generated by this thing. And then in the case that C is presentable again, there's this paper by Getton and Koch where they show that Q is univalent if and only if its index infinity category FQ, right, defined in this way, has a certain sheaf property, namely preserves limits. And we can just generalize this notion then immediately to dropping presentability and keeping completeness by seeing that if C is locally Cartesian closed and complete, and Q is some map, then Q is univalent if and only if its associated index infinity category has a left adjoint. In particular, it always preserves limits if it is univalent, right? Because every left adjoint op, every right adjoint preserves limits. Every right FQ is right adjoint. It has a left adjoint, and every right adjoint preserves limits. The reason for this is that in that paper of Razek, he shows that if we take Q, there is an internal nerve construction to take a vibration, to take a map Q, associate to it a Siegel object, and and then we can externalize that thing. And this is always equivalent to FQ. And then there's the Q is univalent, basically by definition, if and only if this internal nerve is a complete Siegel object. So the first part is definition, and the second part then follows from the results we had before. All right. And then we have the following characterization. If C is locally Cartesian closed, that give me any full and replete comprehension infinity category, then it is small, so it has that one comprehension scheme, if and only if it arises from a univalent map, right? So we can characterize univalence by smallness. Yes. So in other words, a map Q and C is univalent if and only if it is terminal in the core of its associated comprehension category. Now, what that means, in other words, what that means is that if we do not consider it as an object in the core of FQ, but as an object in the full core of all arrows, then that just means that it's -1 truncated in there, right? So -1 truncated in the sense that whenever we have any arrow in C, then if F arises as a pullback of Q, then F is an object of FQ times, and so the Hom space is contractible, right? It's these things are full subcategories, so also the Hom space in the whole arrow category will be contractible. And if it doesn't arise as a pullback, well, it's empty, right? So univalence means it is -1 truncated in this sense. So this suggests.
Can I just ask how much longer do you need?
1 minute.
Okay.
Yeah, I'm done. This motivates the definition for general Cartesian vibrations to define an object to be univalent in there if it is -1 truncated in the core. This has nothing to do anymore with the canonical vibration. This works for every Cartesian vibration there is. And indeed, just by the definition of this, one can retrieve a few results about univalent objects as we know them for univalent maps to hold. And accordingly, one can define the notion of univalent completion by just being the notion of -1 truncation in an infinity category, which is part of the high categorical framework and has nothing to do with type theory in any respect necessarily. Right. So this suggests some work that could hold in a very general setting and could be related to general descent conditions for index infinity categories that have been explored in the ordinary categorical setting, but only have been explored in a very specific case in the infinity categorical world, which is a Rask's descent notion for presentable infinity categories. Yes, and I will stop here. There is some work that can be done for model structures, and some things can be characterized very nicely. The small and locally small index quasi categories are exactly the right equivalent functors into the Joule model structure. And there's some interplay again with the notion of univalence and some notions tied to that, but this will be left for another day. Thank you.
Okay. Could stop sharing your screen, maybe, and we can have a silent round of applause then. Yes, so if there are any questions, feel free to go ahead and ask. Maybe I can ask one question. So if you have a vibration, you construct this collection comp G of morphisms with respect to which the vibration satisfies comprehension. And you talked about some of its stability properties, like push out of monomorphisms and things like that. I was just curious, you didn't mention something like countable composition of monomorphisms.
Yeah.
So you could consider whether this class was some natural thing that you consider a class to be closed on under our pushouts, which you mentioned. Another natural property would be something like countable or transfinite composition.
Yeah.
And I'm curious that you didn't mention.
Well, yeah, I didn't because I just don't know. And the reason is that I didn't really look into it. So the thing is that you want that, the question is if a certain right adjoint exists, right? So you know that the composition of two left adjoints is a left adjoint, and they are under certain circumstances also preserved on a pullback. So these things behave nicely. I don't know about the transfinite. I am not aware of any result about the transfinite composition of left adjoints giving you a left adjoint or something like that.
Yeah, yeah, that's valid. So I think there probably are some results like that.
Okay. Yeah, that'd be nice. I mean, I'd be very happy to incorporate that. So you would drop the finiteness condition in all these
Yeah, I mean, what about, so what sort of vibrations satisfy comprehension for all monomorphisms, or yeah. Maybe one other question. I don't know if I can articulate it very well, but the property of having comprehension with respect to a morphism, it looks like it wants to be the property of admitting certain left Can extensions. If you could put, for example, so on the one hand, you're looking at simplicial sets. They're the domains. So if you have this object rect, say A, B, where A is a simplicial set and B is a fibration. And I'm wondering if you can put A and B into the same 2 category, such that this rect AB is the hom of the 2 category. And so then you're looking, you know, at comprehension properties just as admitting certain Can extensions, and it might, I'm wondering, maybe was that done in the classical setting, or have you seen this?
No, I have not seen that. Yeah, sounds interesting though. Yeah. Yeah, I have not seen that and did not think about that myself, but it sounds interesting.
We can talk about it again sometime.
Yeah, pleasure.
Any other questions?
I just have a very tiny question.
That's good.
I was wondering about this name DAT for the domain of the universal co-Cartesian vibration.
Yeah.
What's the meaning of that?
Oh yeah, well, I just thought it just looks nice with cat and dat, and I thought of that as data. It's infinity data. It worked nicely, and it's basically just an intermediate name, because at some point I proved that it is representable by an internal category, and so from that point on, it's basically just X of delta bullet.
Sure.
Yeah, I just thought it's a nice name for the time being, as long as I use it.
Yeah, I like it.
Thanks.
Okay, well, if there are no further questions, then let's thank Raffael again. And yes, so we have in 2 weeks, there's Christina Vasilikopoulou will give a talk. And if anyone else is keen to speak before then, you can send me an email. But so thanks to Raffael for the nice talk, and we can stop recording now.